So we talked about this equilibrium constant a lot in the past. In this video, we're going to talk a little bit about this thing that's very related to it, which is called the reaction quotient. All right. So the thing is, we're used to writing the equilibrium constant. We're very used to doing that. But the thing about this particular expression is that these concentrations that you put into it are the concentrations when the reaction is at equilibrium. Right? It's possible for a reaction not to be at equilibrium, and if you put the whatever the concentrations there are at the present moment into this, it will not end up equaling whatever that equilibrium constant is. All right. So what you're going to do there is that you're going to have this separate value. All right. The equation looks just the same. It's just that instead of calling it KEQ, you call it Q. All right, which is the reaction quotient. All right. And all that is, it follows the exact same format. It's just that these concentrations are whatever the present concentrations happen to be. All right, so for example, let's pretend that we've got this reversible reaction right here, and I tell you what the current concentrations are. All right, what would the reaction quotient be? All right, well, all you do is you take this and you create your equilibrium expression. You'd have c squared up top, you'd have a squared in the bottom, you'd have b in the bottom, and you just plug in for what things are. All right, and if you plug all those values in, you would get this as your Q value. All right, so the follow-up question is, if the KEQ for this particular reaction is this number right here, would this reaction be at equilibrium? All right. Well, the answer would be no, because if this reaction were to be at equilibrium, once you plug these numbers in, you should get a value which is equal to the KEQ. So the fact that these are not the same is evidence that this is not at equilibrium. So what happens if KEQ does not equal Q? All right, well, it can mean one of two things. All right, either it means there's not been enough time to pass to allow for the reaction to eventually get to the equilibrium concentrations. All right. Another thing that could happen is that there's some other event that's going on that's preventing the concentrations of the reactants to getting to those equilibrium concentrations. And we'll talk a little bit more about that later. All right. So first of all, we'll talk about like the first situation. Let's say that we've got this reaction here, and here's the equilibrium constant. All right. So in the beginning, all we're going to have is A and B. We're not going to have any C yet. All right. And the reason that we're not going to have any C yet is we haven't mixed A and B, and that mixing is necessary for the reaction to occur. All right. So ask yourself, if we take A and B and we mix them together, would there be a point in time where there just hasn't been enough time for these things to react to create C? All right. Or enough C that it would be the equilibrium concentration. All right, and at the very beginning, when this first starts, there just hasn't been enough time to pass. So at that point, if you took what the actual amounts of all these things, A, B, and C, are, and you calculated a Q for it, you'd notice that the Q is not going to equal your KEQ. All right, so what ends up happening? All right. So this is a reversible reaction. All right, so the forward rate, all right, of would be like this. All right, so we could have that rate law. We can define the reverse rate, which would have this rate law. All right, and let's consider what would happen, how these two rates would compare. Well, at the very beginning, when these things are mixed, we would have lots of A and B. All right, that's really all that you would have in the reaction vessel. All right. So since we have lots of that, lots of something times a constant is going to yield a large forward rate. All right, well, what about the reverse rate? All right, that's going to be the rate of this thing going the opposite direction. Well, the rate law for the reverse rate is that rate constant times c raised to the second power. But notice, in the very beginning, the moment after these are mixed, there really is no c. All right, it's going to take some time for the amount of C to build up. So in the very beginning, there's very little of that. So anything times a very small number is going to yield a really low rate. All right. So in the beginning, the forward rate is much bigger than the reverse rate. All right. So what's going to happen if we have a relatively high forward rate? All right. Well, if you have a high forward rate, all right, so this should be a double-headed arrow. If you've got a high forward rate, you're going to start to see the amounts of C build up, but you're also going to see the amounts of A and B go down, because that high forward rate is going to reduce reactant amounts and increase product amounts. So you're going to see the concentrations of A and B are going to decrease, and the concentration of C, the product, is going to increase. All right. So let's say that we were to go back some period of time after these things are originally mixed. Let's say a minute after these were mixed. Well, let's revisit these rates. Well, the amounts of A and B are now lower than they were at the very beginning. All right, and that's because there isn't as much of them anymore. Some of them have just reacted away. All right, so those are lower than before. The amount of C is higher than before, because as opposed to the beginning when there wasn't any C because there hadn't been enough time for it to react, there now has been enough time for there to be a significant amount of C around. All right, so this is now higher than before. So what ends up happening at, like, let's say a minute later, the forward rate has slowed down. The reason that it's slowed down is because you don't have as much of this anymore. All right. By contrast, the reverse rate has sped up because, as compared to a minute before, there's now a lot more of the C around. All right. So what happens is that the forward rate over time is going to start to slow down, and eventually the reverse rate is going to speed up. And this is going to continue until they eventually are going to equal each other. All right. And at that point, when they equal each other, this is going to be the point where the reaction is considered to be at equilibrium, and at that point, KEQ would equal Q. So one thing that you're going to be responsible for knowing is recognizing some graphs, all right? And two of the graphs that are going to be concentration versus time and rate versus time for an equilibrium reaction. All right, so if we're going to do concentration versus time, there's two ways it might look, all right? So the thing about a reaction at equilibrium, there's two things that you can say, is that number one, the forward rate equals the reverse rate, but another thing that you can say is that at equilibrium, the concentrations of the species in the reaction are going to be staying the same. All right, that's not to say that the concentrations are going to be equal to each other, but whatever those concentrations are, they get to a point and they just stay that way. All right, so let's say at time zero, we're just measuring. Let's say that this line represents the concentration of a reactant, and that this line measures the concentration of a product. Well, in the beginning, you don't have any products. All right, and remember, by products I mean the thing on the right. All right, and let's just say that we're starting with all. For example, let's say that we're starting with all. Let's use this as an example. All A and no B. All right, so all A and no B. So what that would mean is that in the beginning you have all the reactant and you have none of the product. So over time, your products are going to start to go up, but they're eventually going to get to equilibrium. At equilibrium they stay the same. Your products are going to, your reactants are going to go down until they get to the point where their concentration stays the same. So notice at the end, it's not that they're equal to each other, it's just that whatever they are, they're staying the same. All right. Notice it could have been a situation like this, where these two lines would cross. All right. You know, either of these situations, you'd have the same thing. They eventually get to the point where, in the end, their concentrations are staying the same. All right. If we're going to do the graph where it's rate versus time, remember that when you have something in equilibrium, the thing that's going to be true is that the reverse rate equals the forward rate. So whatever that rate is, so remember, as this reaction right here progressed, the forward rate started slowing down over time. So that's what this shows. Over time, that forward rate starts going down over time. And remember that the reverse rate speeds up over time. So that would increase over time. But the one thing that you need to make sure that you recognize is that they eventually get to where they are the exact same thing. All right, that is the definition of a chemical equilibrium. It's a reaction where the forward rate equals the reverse rate.